Hello. Here I'll be tackling a related rates problem involving the velocity of a piston. Really quick. Related rates are problems involving variable quantities which are changing, typically with respect to time. You are tasked with finding the appropriate equation, implicitly differentiating, and finally, plugging in the given information to extract the solution. Here's the question. A 7-inch connecting rod is fastened to a crank of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of the piston when angle theta is equal to pi over 3. First, if you're like me and are unfamiliar with the mechanism being described, it would be beneficial to first investigate the appearance of a piston, connecting rod, and crankshaft. Here's an example. Now let's observe a simpler animation of one of these in isolation. Now it's a bit easier to look at. Let me pause the animation and bring the problem back into frame. A quick search will show that this part is the piston, this is the connecting rod, and this is the crank. The crankshaft is perpendicular to the picture, and it is essentially a rod that will go through this hole. The crankshaft is also the part that is rotating counterclockwise at the given rate of 200 revolutions per minute. Let me simplify the picture even further and attach the given values to their rightful places. Hopefully by now you have identified the triangle that forms when we drop an imaginary line here. This is important because it helps us identify the changing variables for this particular problem. We can easily identify one changing variable as the angle theta. Recall that this mechanism is always rotating, and so theta is always changing. But what about the other one? What is our other changing variable? The question asks about the velocity of the piston, but the piston is over here outside of the triangle, touching the rightmost vertex. So how could we understand the velocity of the piston as it relates to the triangle? Observe the imaginary line we drew and see how it connects to the piston, and recall the rotating motion. The imaginary line is always changing length. Now, could it be the case that the rate at which this imaginary line changes length is equal to the velocity of the piston? And yes, that is the case. The velocity of the piston is the rate at which the base of this triangle changes length. This is a key realization, one that isn't very obvious. Two more things before beginning the problem. First, now that we've identified the changing variables, we need some equation, some formula that relates the angle theta to a side of a triangle. Luckily, we have the law of cosines, which looks like this. And two, we need to address the given rate at which the angle is changing and convert revolutions per minute to radians per minute, since theta is in radians. Also, since we are now working with a trig function, it's best to stick to standard inputs, so we will convert to radians. Recall that the question asks for the velocity of the piston, and because the velocity of the piston is the derivative of x with respect to time, let's use the formula we've identified as the law of cosines and implicitly differentiate and solve for the derivative of x with respect to time t. Notice that in this equation, we need three things. We need the derivative of theta with respect to time, which we have. We need theta, which is pi over 3, and we need the length x. This is the one thing we don't have, and we need to find it. Let's use the law of cosines again with theta defined as pi over 3 and simply isolate x. Here we have it. X is 8 inches when theta is pi over 3 radians. Now that we have all three pieces of information, we are ready to input them into the derivative of x, and finally, we'll have the velocity of the piston. And of course, don't forget the units.